All modern house walls have two faces with still air in the middle and don't lose much heat. Doors are different. A thick, heavy door loses heat as rapidly as a thin sheet of plywood. The physics of heat transfer shows why. Heat is the vibration of matter. This picture represents a cross-section of a door. The blue circles are molecules. They are vibrating even at room temperature. Only at absolute zero, which doesn't exist anywhere in the universe, would all vibration stop. The warmer the temperature, the greater the vibration. Heating one side increases the vibration of molecules at the surface. Those deeper in the material are not affected directly by the outside heat, but they are affected by each other. The molecules just below the surface absorb some of the energy, and they in turn get hot. This continues through all layers, the heat moving like a wave from the hot to the cold side. The closer the molecules are to each other, the stronger their mutual influence. The wave moves fast through the solid door, but what happens to this heat wave when it reaches the other face? It's not a vacuum out there. It's air, and air comprises molecules, but they are much further apart. The heat wave continues moving, but much more slowly. The difference is so dramatic that we give it a different name. Heat flow through a solid is called conduction, while through a gas is called convection. The air absorbs so little energy that the heat wave crashes into the face like an ocean wave against a cliff, but it doesn't bounce back. Instead, the excess energy is transformed into infrared radiation, which streams off at the speed of light. It's not a coincidence that this electromagnetic radiation is of the same frequency as vibrating matter. While the heat leisurely strolls through the air by convection, it instantly escapes by radiation. Either way, the door loses heat until it and the outside world are at the same temperature. We can't stop this. To reduce heat loss from the room, we need to do something inside the door. Unless we want to make it like a wall, we have to do something to its inside face. Just as the outside face loses heat to the world by convection and radiation, the inside face gains heat from the room. Ironically, making the inside face colder will make the room warmer. All material absorbs heat, so we can't stop this, but radiation can be reflected. We can completely stop the infrared heating by covering the face with aluminum foil, but we don't know how much it is being heated by convection versus radiation. One door of my house is a good test candidate. It is an old barn door, intended more to prevent the escape of horses than heat. On a cold day, its inside face is cool, but considerably warmer than the outside air. It's already a pretty weird door for a house. Aluminum won't make it much weirder. We can use the thinnest aluminum foil because reflection occurs entirely at the surface. It's glued to the door with contact cement. Solvent-based cement works best, but it is impossible to clean up, so I use a cheap throwaway brush. Disposable gloves are essential. They must be nitrile because the glue dissolves latex. Complete glue coverage is not required on either the foil or the door. It's best to do this on a warm day when the glue flows easily. The air temperature must be at least 60 Fahrenheit. Below this, the glue turns into gum. The foil can be flattened onto the door by hand, but I'm using a rubber block printing roller to squeeze the aluminum into the grain of the wood. I just like the way this looks. It won't influence the function. Depending on your point of view, the finished door is either hideous or interesting. In my house, it's just one more strange thing. But does it work? The proof is in the door. When it's cold outside, the inside of the door is much colder than the rest of the room. It clearly is sucking less heat out of the room than before. It seems that radiation, rather than convection, is at the root of most of the heat loss.